Rare earth elements are used in what are termed rare earth permanent magnets, and those magnets are used in clean energy applications and electronics such as wind turbines, e-mobility, and things like hard disk drives. So there are rare earth neodymium iron boron magnets within hard disk drives. There are actually two applications that use that material. There are sintered neodymium iron boron magnets in the voice coil assembly here, which controls the read and write arm over the disk. And there's a second magnet in the spindle motor at the top of this hard disk drive. And basically, the magnets are used in the motor to control the read and write arm over that disk. So the rare earth elements are often top of what are called the critical materials lists in many countries around the globe. And that means that they're economically important, but at risk of short supply. So if you want to recycle a magnet in this hard disk drive, one of the problems at the moment is that the disks at end of life are typically shredded. If you shred this disk at end of life, and they do that to destroy the data on the disk, the magnet in this component here is extremely brittle and it breaks apart, but it stays magnetic. So the powder you generate during shredding sticks to all of the ferrous components in the machinery and to the ferrous components in the waste stream. And that makes it extremely difficult to separate. And that's one of the main reasons that less than 5% of these magnets are recycled globally. Once the corner of the drive is removed, we used a process called HPMS, which is patented by the University of Birmingham and licensed into HyProMag. Essentially, what the HPMS process does is it breaks the magnet down in hydrogen so that it absorbs the hydrogen gas. The material breaks apart into a demagnetized powder. The coating peels off the surface of the magnet, it removes it from the glue, and simply by tumbling the electronics, or the corners in this case, we can remove that demagnetized powder, and we can do that on a very large scale. So the separated neodymium iron boron alloy powder, we can purify that downstream to a point where we can directly remanufacture that material back into new sintered magnets in a short loop process. And that only requires 12% of the energy compared to primary production without any of the chemical byproducts or waste. So the biggest problem for magnet recycling is that you have a separation problem of the component from the drive, as an example, and then to separate the magnet from the waste stream. These two technologies offer a solution to both of those problems. In doing so, we would then provide a feedstock of neodymium iron boron to the US market, but also we would bring magnet manufacturing expertise to the USA.